yeah, yesterday I got a notice from my Corona One app that I have a positive contact. So I have a red one app, and as you know, in that case, you should be careful and stay at home and first take a test. I feel good. I guess everything is fine. But anyway, probably it's better to stay here and to give the lecture online only. Sorry for that, but I guess in the meanwhile you get use of this this bad situation. Anyway, let's try to make the best of it, and yeah, I would very much appreciate if you would give some comments or remarks or questions during the lecture, that it is as interesting as possible. Good. Any remarks first of all concerning the lecture or any other topics? Okay, this seems not to be the case right now. I hope all of you feel fine, and I hope that my Red Corona app was not according to the last lectures and you have the same problem now. Yeah, let's start with this lecture today. It's the last lecture with some content about some new content, and as you can see, we will talk about bubbly flow together now. Bubbly flow as one application is a bubble column, and so we'll talk about bubble column reactors and the application of bubbly flows. This is one of the processes that can be used for the chlorination reaction that you have for your examen and the PBL examen. So probably some of you have already used the bubble columns for the chlorination reaction in your PBL, and therefore you might have in some points more knowledge about that than myself. So please don't hesitate to interrupt and to give some comments or questions if this is related directly to your PBL. So you know, that's something I very much like in this lecture. At the beginning, you don't know so much about the reactors, and then you'll see more and more about that during this semester. And now at the end of the semester, probably in your own process, you're much more deeper than me, and this is always a nice experience as well for me, that you get more and more experienced with these reactions and the multiphase reactors. So let's talk about application bubble column reactors, and as in the last three lectures, you will already see some points that are already known, because we have already talked about hydrodynamics and mass transfer and reactions and so on. But anyway, I will repeat this briefly today, because I guess it's good to see this once again in the view of a special application. In that case, it's the application for bubble column reactors. So once again, here we see this Ineos phenol company in Gladbeck. They are producing a huge amount of cumene in these bubble column reactors, and you see that we have here 5 reactors in a row and 3 in parallel to get the sufficient productivity for these mole production here in Germany, in Gladbeck. And here's another example, bubble column reactor at the Evonik industry. So in Marl in Germany. So these are the reactors we're talking about today. And here you can also see the usual height of these reactors. Yeah, maybe you can estimate a little bit with these trees here around the columns. So they're in the range, usually in the range of, let's say, 50 to 20, 25 meters in height, and 1 to 2 meters in diameter. This is a typical shape of these columns, and for sure they are tall. Bubble columns are always tall, because we want to use the buoyancy-driven flow by the gas bubbles to get an efficient mixing in the systems, and therefore they are not course, so we have an aspect ratio of around about 5 to 7 for this kind of reactors. So 7 times the diameter is the height. So to give you some insights into the necessity to design and operate bubble column reactors more efficiently, it's nice to look on a typical reaction that is performed in bubble column reactors. And here you can see a catalytic hydroformylation reaction. It's a bulk product that is used for example, for polymer polymerization reactions is one example. And you see here the huge amount that is necessary. So the worldwide production capacity of 6 million tons per annum. This is a very old number, 20 years old. I guess today it will be much more. And here you can see how this reaction has been optimized in the last centuries. So, for example, we have here in 1983, as this process was developed for the first time, there was a catalyst that needs 150 to 180 degrees Celsius and 200 to 300 bars pressure to come to an optimized and efficient reaction. And you see in the course of the years, so here, for example, 30 years later, we have higher temperatures, but already much lower pressures, because you can imagine to create pressure, this costs a lot of money. So our intention is to decrease pressure in temperature as well. So 30 years later, we had a lower pressure here. And further later, we have today already in the range of only 10 to 50 bars that are necessary to perform an efficient reaction. And especially the temperature has been dropped dramatically to only 60 to 120 degrees Celsius with the same efficiency. So this is a very good story. And of course, in future, we would like to come to a much lower temperature and also lower pressures to save even more energy. We always have to think about climate change in the further developments, and therefore let's try to bring them further down. And there is already a biocatalytic process with this organism here. And with this organism, we can use the bioprocess with ambient temperature and also ambient, more or less ambient pressure. So 37 degrees Celsius for these bioprocess and atmospheric pressure. And this is why more and more processes are shifted now to bioprocesses, because we have here much more sustainable processes usually. So what does it mean at the end? We see that the temperature and pressure goes with the timeline further down. And of course, in the same way, we try to enhance the activity and the selectivity of the processes to have a much better performance concerning raw materials and concerning the quality products and also sustainability. So we are on this line here. But what does it mean? It means if we have much more activity and selectivity in our reactors, then this means that we need a better transfer performance as well. Yeah, the reaction itself is a sink for our raw materials, for our educts. And if the reaction gets faster and faster and faster, and this will be done by nanotechnology, biocatalysis, and so on, so more efficient catalysts will be developed in future. This means the sink and where the reaction takes place is much, much stronger. But what does it mean? This means that even more educts have to be transferred to the catalyst, and vice versa. The product has to be transferred from the catalyst away. So in other words, much more efficient processes driven by chemists and by biologists. This is only possible if the process engineers are able to have such a good performance in the reactors that we can have an efficient mass transfer. the whole process is only as fast as the mass transfer is at the end, if we have fast reactions. And you see, this is the reason why I would like to discuss with you today about these bubble column reactors and where are the limits for mass transfer in bubble column reactors, and what can be done to overcome these limits and to make mass transfer coefficients, mass transfer performance of multiphase reactors, here as an example, the bubble column reactor, much more efficient. This is our motivation for today. And the question is, how can we improve mass transfer in bubble columns? And I guess you already know this from this lecture. So here's once again this picture of a bubble column where the bubbles are formed here at the bottom. Then we have bubbles that are rising in a certain structure of swarms through these column. We have a certain gas void fraction. We have the gas liquid mass transfer. Here we have an axial dispersion of gas in the system, and coalescence and breakup mix takes place for these bubbles. So this is how the system looks like. And you already know that the interfacial area for the mass transfer is one of the most crucial points and one of the most effective parameters that we can try to enhance the mass transfer as well. So the interfacial area for transfer, it's the same for heat transfer than for mass transfer. This interfacial area, this has to be increased. And of course, first it has to be known how large this is to come to an efficient process. So what are the key parameters for gas liquid mass transfer? Of course, it's the interfacial area. Here we see the equation once again for that. We have the mass transfer that is transferred, the mass that is transferred per reactor volume. And you remember we already had this equation several times. So the volume-specific mass transfer, small m dot, is the mass transfer coefficient multiplied by the interfacial area multiplied by the concentration difference. So this is a saturation concentration. And here we have the concentration in large distance from the interface. You remember this equation. And already from this equation, you can see that A is a crucial parameter, and we can estimate this A with this simple geometric assumption here. We have 6 multiplied by the gas hold up divided by the solder diameter of the bubbles. We already talked about that. But if you look on that more carefully, then you see from this equation and that equation that obviously the mass that is transferred, what we are interested in, this might be the mass of an e-duct, for example, oxygen that has to be transferred to a biocatalyst to transform a certain product. So this is a mass flow rate. This is directly proportional epsilon to the gas hold up. In other words, if you have a deviation in gas hold up by some reasons, for example, viscosity changes or blocking of your gassing system or whatever, if you have 20% deviation in gas hold up, then this means that you have as well 20% deviation in mass transfer performance. And of course, if you have 20% deviation in mass transfer performance, which means that you have 20% less oxygen, for example, that is shifted to the catalyst, then this means you have 20% deviation in conversion. So you have 20% less product at the end of your process if you have 20% less gas hold up. Yeah, so this is a very crucial point and makes clear how important it is to let's say, to know the gas hold up and also to increase the gas hold up. By the way, this is of course only valid for mass transfer limited reactions. Yeah? If the reaction is so slow that you need several times, several hours, or maybe days for conversion, then of course a mass transfer is not the limiting factor. But as I mentioned in the slide before, in future, of course, you want to come to higher conversion processes, and then this gets more and more important, and the gas hold up gets more and more important. So this is our top priority for better models. The top priority is to predict the gas hold up for industrial conditions. Yeah, now you might say, what does why is it so difficult? We have processes in chemical industry that are running very successfully for many years, and it seems to work. So what is the problem of that? And to show you this, how critical this indeed is still, I would like to show you some original slides from the company Evonik. And the company Evonik, some of you might know them, and I know we have a group of Evonik. So it's a well-known, large German company, chemical company, producing a lot of basic chemicals. They have a lot of experiences in designing and running reactors in Germany and all over the world. And therefore, they really know what they do. So we can be sure that they know what they do and that they have a very good overview of opportunities and possibilities to design and to set up reactors. And these are some slides that have been presented some years ago. You see 2013, but anyway, it's still the same problem. So this company showed us slides here about the oxidation of cyclohexane. And for this cyclohexane oxidation, it's a very important and huge process as well for a very huge product. And you see that usually we have the influence here of the gas hold up. So this is on the one hand side the gas hold up. Sorry that the slide is in German, but it's the original one. So we have the gas hold up on this axis, as well as the yield here. Yeah. So red is in purple here is a gas. In gray is the gas hold up. In black we have the yield, and in purple is the selectivity, and the selectivity is given here. And what we can see is for the same process with the same parameters, here 3 different correlations for predicting the gas hold up has been used. One correlation is from Wilkinson, one from Edogawa, and one correlation comes from Rayleigh. And all these correlations use the same basic data. So the basic data for all the correlations is the same. And from the publication on, all correlations should be applicable to this problem. There is no restriction in this correlation to apply the correlation to this problem. So my colleague Mark Becker at the Evonik company has used these 3 correlations and has applied that to this special problem, to the cyclohexane oxidation, and he calculated first the gas hold up. And as you can see, the gas hold up from Wilkinson says, okay, the gas hold up is 5%. With the correlation of Edogawa, we reach 10%, and the correlation of Rayleigh, he predicted for this process 20% gas hold up. So 4 times higher gas hold up in these 3 different correlations. And remember what I told you before, 4 times higher gas hold up means 4 times higher mass transfer performance, means 4 times higher product at the end, if this is a mass transfer limited reaction. And it is, cyclohexane is a very fast exothermic chemical reaction. So in other words, your reactor can be 4 times smaller if you calculate correlation, use correlation from Rayleigh, than by using the calculation of Wilkinson. And of course, as good engineer, now you will probably say, I will be on the safe side of life and will use the Wilkinson correlation, and let's build the reactor 4 times higher, and then I'm safe. Okay, but on the other hand, don't forget 4 times higher volume means 4 times more energy to drive the system, 4 times more e-ducts that you have to feed into the system, more energy that is necessary to clean the product afterwards, to purify it, for example, by thermal processes like distillation or something like that. So you can be sure that your process will be much more inefficient if it's scaled too large. And another point is, if you look to these calculations for this process, then you see that the yield decreases with increasing reactor volume as well. And also, and this is more critical, the selectivity drops. the selectivity, so the amount of product in comparison to unwanted byproducts, decreases also strongly, dramatically. Let's say here from over 90% to less than 80% or 80%. So this is a dramatic drop in selectivity, and this that more products here that have to be separated in thermal processes like distillation or something else. So this means you have much more waste and much, therefore you have used your raw materials much less effective, and also you need a lot of effort and a lot of energy to clean up your product here, because you have so much waste in your product. Yeah, and but what should you do? Because if the correlations are saying a deviation of 4 times different gas holdups, what should you do? What can be used? What kind of correlation? As you can see, this is very critical, and it's a few years ago, and unfortunately we don't have so many better correlations so far. So this is one of the top priorities that we have to be solved in process engineering, to come to more efficient processes for a more sustainable future, to have this under control. Yeah, and here we have the same. You can see that even with different with one correlation here, the Wilkinson correlation. So this Wilkinson correlation has been used, and you see that if we use this Wilkinson correlation, then we can come up. If we use here, for example, the axial dispersion. So this is another point that is not very often taken into account. If we take this additional information into account, then even with one correlations, we have very, very different results for the yield. You see the yield is here 3.5, and here the yield is 0.5. And here we have the selectivity in between 94 and 88. So even if we use one correlation, even this one correlation has still a lot of uncertainties. And in this case, the uncertainty is here this axial dispersion coefficient that has been changed. You might remember the axial dispersion coefficient is the coefficient that says how strongly does the bubbles distributed in the column, and how strongly is the column mixed in the axial direction. The axial dispersion coefficient is very low if we have more or less a plug flow reactor, and if it's well mixed, then we have a very high axial dispersion coefficient. And this can be estimated here with this correlation. But it's difficult. You need to know the superficial gas velocity, the gas holdup, and here you need these DC, which is a coefficient that gives you this axial dispersion coefficient that has to be estimated. And you see, it's of course it's difficult to estimate this axial dispersion, and even this parameter changes the yield from this from 3.5 to 1.5 or 1. Now you might say, okay, it doesn't matter what is the problem, but the problem is, if you look on this graph here from the Evonik company, then you see an example calculation for the productivity of the whole plant. And here these cyclohexane oxidation has been calculated for a productivity from a capacity of the plant of 330 kilotons per year. And in that case, the gas holdup has been calculated by Wilkinson. And here is a price for 1 kilogram of cyclohexane. So it's $1.82. And now it has been calculated how much product is produced by, if you assume these different gas holdup correlations. And these are the gray lines, and you see that with a deviation of -20 and +20%, we have 2 kilotons per anno product, or just a little bit more than 0. And with Ito-Gawa and Rayleigh's correlation, we produce, because we have much higher gas hold up, we produce, of course, much more product here. So here we have these factors once again. And it's a very strong influence. And more dramatically is if we calculate our what we earn from this production, and you see that here we have, this is in the value of our product in $1 million per annum, and you see here we have $2 million, $10 million, $5 million, and yeah, probably it's not worth to run the process with Wilkinson at all plus 20%, because we're just a little bit above $0. So probably it's more costly to drive the plant and to pay for the equipment than running this process. Yeah, so this, I guess, makes clear that it's not very funny that we don't have any correlation that is really reliable on, or in another way, it's a very big risk for you as engineers to design a plant and to decide which kind of plant structure, size, and so on you need to have. This shows the big risk. And this is why one of my colleagues at the BASF company told me that before he is running a new process in reality, after the scale up and the design process, before this process starts to run, he never sleeps the night before. Yeah, because he's always very worried that there might be something that he has not taken into account, or that one of the correlations that he used is not reliable, and therefore we have still in process engineering a very huge risk to make such kind of mistakes, and then troubleshooting starts, and everybody tries to find out what is the problem and what runs wrong here at this point. And as you can see from this example, the gas hold-up prediction is one of the most critical points. And this is why, and you know our product with China, I showed you these movies already. This is why we do these experiments in China, to see if the system is behaving similarly to the system with water and gas at our laboratory, to get a feeling how reliable our correlations might be to predict the gas hold-up. So this is an important message for you, I guess, for the design of bubble column reactors. And and there are, of course, several reasons why these correlations are so unreliable. One reason is that most of the correlations have been derived for empty columns, like here on the left-hand side. This is a typical simple equipment for a laboratory experiment. And you already know how to measure the gas hold-up here. In this case, we can measure that aerated system, the gas system. Then we have a high liquid level. And if we use a gassing out method, then the gas runs out of the system, and with that, the level decreases. And if we have a cylindrical system, then we can calculate the gas hold-up just by the difference of the upper level and the lower level, so with gas and without gas, divided by the height of the gassed system H. And this is our gas hold-up. Very easy, very simple. And now we can use this to get this correlation, gas hold-up independency of the gas flow rate, or maybe liquid flow rate. We talked about homogeneous and heterogeneous regimes. They very strongly influence the hold-up, as you remember. But usually in industry, your system does not look like this, not this simple. Usually you have systems that are much more complicated, like you can see here on the right-hand side. For example, you have different gas distributors. You might have a nozzle here, a jet. You might have some internals like a draft tube. You might have internals like a heat exchanger. And all this strongly influences, of course, the gas hold up. Very often you have the top of the reactor is here a little bit expanded to give the gas more room for gassing out. All this is not taken into account usually in these correlations, of course. So this is why often it's necessary to do laboratory experiments or even pilot plant experiments, what is much more effective and reliable, and then to adapt the correlations, and with the adapted correlations to pray that they will be applicable as well for a larger scale. This is how it works. Good. This homogeneous heterogeneous flow we already discussed is an important point to distinguish between different flow regimes and therefore different gas hold ups, mixing states. Here we have a very low axial mixing. We have a very strong axial mixing. This is something that needs to be predicted usually, and we already saw this diagram that you can see this transition from homogeneous to heterogeneous regime with the gas hold up, because here the gas is rising slowly and homogeneously, so the gas hold up can get quite high, as you can see here. And if you increase the gas hold up too much by increasing the superficial gas velocity, then it comes to more and more coalescence, because the bubbles are not able to rise fast enough to transport all the gas that is fed here at the bottom to the column, and therefore coalescence happens, which makes the bubbles even much faster. But faster bubbles means lower residence time, means lower gas hold up, and this is why the gas hold up decreases here. So we can use this measurement here to identify the transition from homogeneous to heterogeneous bubble regime. And this, of course, depends on the diameter of the nozzle and other geometries and other circumstances. So another point that you need for the design of your bubble column is the pressure drop that is necessary to drive the column. And the pressure drop can be calculated with the liquid height. Actually, it's a liquid height, and this static height of the liquid is the most important factor for gas hold up calculation. And this is here in our delta P total. This is here the two-phase static pressure drop. Yeah, so how much pressure do we need to overcome these liquid column? And then we have additional pressure drops. We might have additional pressure drops in the bubble column. That is, for example, the friction. The bubbles have some friction, of course, and with each other and with the liquid. And another point might be the dynamic pressure drop that comes from the expansion and from the shrinking of the gas phase. Yeah, expansion might be due to the decrease of the pressure. If the bubble is rising, pressure decreases, and the bubble might expand, and this means the bubble presses more liquid away through the distance between the bubbles, or also we might have evaporation, and this also, of course, increases two-phase pressure drop here. Now we had this already discussed, and we already saw some equations. So we have the single-phase pressure drop that can be calculated with common equations, and we can also use calculate the friction factor. Here is the equation of Friedel. Again, I don't want to repeat that because we have talked about that several times. And we have sometimes a pressure difference by gas hold up. For example, if we have a draft tube and we have a downcomer and a riser, then you might remember if a bubble is rising upwards and the liquid comes from above, then the bubble is slower in the velocity, so the velocity decreases, which means gas hold up increases. And if we have co-current flow like in the riser with the same direction of the liquid with the gas bubble rising velocity, in that case we have a faster bubble, and faster bubble means lower residence time, means lower gas hold up. So higher gas hold up, lower gas hold up. And this means we have in between the draft tube and the room out of the draft tube, we have with countercurrent and co-current flow, we have a pressure difference, and this pressure difference has to overcome with some momentum that comes from feeding the gas into the system or using a nozzle or whatever. So therefore, this relative velocity of the bubble is very important to know, and therefore we can calculate this here with superficial velocities and gas hold up. So this is the static pressure. Yeah, and there are several correlations for estimating the gas hold up. What you probably remember are Akita and Yoshida. They have derived many equations for hold up, for mass transfer performance, and so on. And they are usually quite reliable, and therefore this is one that I can recommend, for example. And for yourself, for your future, I can recommend you always to look on these equations carefully, how much parameters are taken into account. Because the more these correlations are depending on empirical parameters that have to be adapted, the less reliable is this equation if you transfer the equation from one system to another system. Yeah, because these parameters here, for example, this is an empirical parameter, this is an empirical parameter, they have been adapted with experiments that have been done somewhere in the laboratory under very special conditions. And if you change the conditions to your own system in industry with a certain chemical system, certain gases, other temperatures, other pressures, then you don't know if these constants that have been adapted are still constants. So if you have physics inside of the correlation, like in this case here, or Akita and Yoshida, then it's much more, probable that you will be able to transfer the equation. Here, for example, this seems to be applicable to different surface tensions. Yeah, and this means if you have a changing surface tension, then it might be that the equation is still okay. If you use this equation here is no surface tension taken into account, so the Bach and Pirhofer correlation is probably not very useful if you have changing surface tensions. And as we know, the surface tension strongly changes the gas hold up. So this is one example. Or on other way around, this has been derived for air alcohol solutions. And air alcohol solutions, there usually you have very small bubbles. And if you have very small bubbles in your system as well, because you use surfactants, for example, then this might be applicable. But for other systems, it might be quite critical. So this is how you should look on these equations. So another nice picture is this one here. We used not only these three equations that have been shown by the Evonik company, we used much more equations. Here you see different gas hold up correlations. Some of them have been already announced. And you see here the gas hold up, the superficial gas velocity, and these are the results. And all these correlations should be applicable to the special process here. You see, this is a whole bunch of different gas hold ups, and it's extremely difficult to decide which correlation should be used here. And another example comes from one of our international master students here, Emilio Nasembesini, from Gonzaga in Italy. He was at our institute and wanted to make a project work, and he did some gas hold up measurements in always the same bubble column, but with different water. And so he used the conditions of his own water from his hometown in Italy and from Milano and Los Angeles, Hamburg, New York, Boston use different tap waters. Don't understand me wrong. It's just tap water from the tap. Same temperature, same pressure, everything the same. But you see just from the conductivity here that even tap water is very, very different. And also some minerals, of course, are different in the different tap waters. You have different water hardness in the different tap waters. And if you compare the gas hold up just with different tap waters, and we compare this here with distilled water, then you can see that there's this very strong difference in between these different waters. And if you see that, then it's not very surprising anymore that the correlations are so different, because many of the correlations are derived with tap water. And this means that if we have another tap water quality in Hamburg than in New York, that probably our correlation will not work in New York just because of the tap water quality. And this is not negligible here. You see 30% and 60%, so 3% difference in the gas hold up here. So this was a nice work from Emilio, and I always like to show this very simple experiment, but I guess it's very impressive to see how sensible the gas hold up for watery systems is. So what are the status quo with gas hold up correlations for these bubble columns now? So the problem is that only extrinsic parameters are taken into account for the correlation. So we have only the superficial gas velocity that is used, surface tension, viscosity of the liquid phase, the reactor dimensions, and we have unfortunately no possibility so far to take into account so-called intrinsic parameters. So parameters that are inside of our system. So like the interface mobility. One problem is if we have surfactants, then these surfactants affect the interface mobility and the local bubble velocity. Then local energy dissipation rates like turbulence is usually not taken into account for these hold-up correlations, because as we know, if we have a very turbulent system, we have very strong shear stress and we get very small bubbles. And this brings us to a larger gas hold-up, but this kind of turbulence is usually not taken into account in these correlations. I go back to the correlations to show it to you. So where is here turbulence taken into account? Of course, we have the superficial gas velocity, and maybe that this is directly related to the energy dissipation rate and turbulence, but you will probably agree with me that this very strongly depends on the size of the reactor, if this really creates turbulence here or not. And it depends on viscosity and the homogeneous distribution of the gaseous phase and very, very many other parameters. So these extensive parameter, the superficial gas velocity, is not able to really give us an idea about the intrinsic parameter of the turbulence. Yeah, and also, as already mentioned, internal geometries are usually not taken into account, like sparger design or obstacles like baffles or heat exchangers or something else, because there is such a huge variety of different designs. It's nearly impossible to derive correlations that take care about all these points. So what we have at the end is a bubble size distribution that is unfortunately more or less unknown, but this should be calculated to be more reliable in the correlations. Okay, so far for the importance of bubble size distribution and gas hold up in bubble column reactors. Do you have any questions or comments so far? Okay, this seems to be not the case. Then I would like to continue. So the first point is we talked about these bubble diameters that are important to know. And we already saw this diagram. There are some opportunities to get bubble diameters from the dependency of viscosity and here the hole size and hole pitch. So this was the distance between the holes. There are some correlations and also some graphics like this one here to calculate these bubble diameter. And here we have another opportunity for different surface tension. I mentioned surface tension has this strong influence of the bubble size. Here from 7 millimeters it drops to 4.5 just with decreasing surface tension. So there are correlations and also such diagrams, but the problem is that we always can only get one diameter out of this diagram, and this is a mean diameter that can be calculated. But as you know, we have always a distribution. We have smaller bubbles, larger bubbles. This might be the mean diameter, but how broad the distribution is almost unknown and very important, of course. So with these overall bubble diameter, this diameter estimation, we can go into these correlations that we already discussed for calculate the bubble velocity. So for the calculation of the bubble velocity, we use these different dimensionless numbers here: fluid number, Archimedes number, fluid number, and Reynolds number. And as you can see, the diameter is here one important critical point, or let's say the most important critical point: bubble diameter and bubble velocity. And now we can use such correlations here that we have already seen to calculate the drag coefficient, and with the drag coefficient we can calculate the bubble rising velocity. And you also remember that the bubble rising velocities are changing. So they are first rising. If the bubble is spherical, then we have a shift in the shape of the bubble to ellipsoidal bubbles. The velocity decreases, and then with further increasing diameter, we come to formless shapes and constant rising velocity again. So please keep this slope here in mind, this line in mind, how it looks like, to be able to draw the dependency of bubble velocity from bubble diameter. And please don't forget, this is a double logarithmic scale here, yeah? This is double logarithmic. Okay, and of course you don't need to have this equations here in mind, but it's good to know that there are equations and that you can look it up and can calculate bubble rising velocity in dependency of a certain bubble diameter. If we go back, then you see here we have a very simple approach, the linear dependency 24 divided by Reynolds. This is typical and also well known for spherical particles, solid particles. And if we have internal circulation of fluid particles, then the drag coefficient decreases here to 16 divided by Reynolds. Yeah, and another remark is, of course, here you have the Reynolds number inside of these correlations always. And the Reynolds number contains the bubble velocity, and that's what you would like to calculate with this correlation. Yeah, so this means you need to iterate here. In this case, you need iterations to calculate the bubble velocity, which is not very difficult, by the way. Okay, and now you have for your design of the bubble column reactor an estimation of the bubble diameter. Of course, you know it's not very satisfying and reliable, but anyway, we can try to get this bubble diameter. We have calculated the bubble velocity, but now to come to the residence time of the bubbles in the system, we need to know the velocity not only of the single bubble, but we need the velocity of the whole swarm. So how can we calculate the rising velocity of the swarm? And in that case, as you can see, we have this liquid that runs inside of this bubble swarm. Because the bubbles are rising, they are depleting liquid, and the liquid has to go somewhere due to the continuity of mass. And this means that the liquid that is depleted here by the bubble that goes upwards needs to go through these bubble swarm here. So the higher the bubble rise, the faster is the velocity here in between the bubbles. And this means this introduces this kind of countercurrent flow. This has to be taken into account. And this is taken into account, for example, here with this correlation of Richard and Zaki. Here you can see this is a single particle velocity, 1 minus epsilon to the power of n. And this means that the higher the gas hold up, the lower is the swarm velocity due to this countercurrent flow. And with this factor here, with this exponent, we can adapt the situation to the equation to several situations depending on turbulence, for example. For laminar flow, we have another exponent than for turbulent flow. This is a famous correlation from Richard and Zaki that takes into account this swarm velocity. By the way, to show how relevant this still is, even that this is a correlation from 1956, yesterday was a PhD defense at the Institute of Professor Heinrich, and the PhD student had to draw these Richard and Zaki law, because even for solid processes, of course, it's a very important equation and needs to be known. So there are other more complicated correlations, but I don't want to mention that now. But this is the most important one here. We have 1 minus epsilon to the power of something. And the problem is that these correlation, all these swarm correlations are assuming that the particles, or let's say the bubbles, are distributed homogeneously in the system, like here. Otherwise, this geometrical correlation here does not make any sense. And here we have another critical point, right? So how can we make sure that the particles are distributed in this way? And of course, in reality, they are usually not. So therefore, this correlation is somehow questionable. But we don't have any better one. So, and I promise you, during your career as engineer, you will extremely often come to this point that you have to say, okay, I know the correlation is not very reliable and not applicable to 100%, but anyway, I don't have anything else, so I try this. I try this correlation, and I use this correlation. The reason why I use this correlation is A, B, C, D, and you know, you have the uncertainties of A, B, C, D, but due to the lack of a better correlation, you use this one. Yeah, and I promise you, your supervisor, your boss will be satisfied with that if you do it like this. And you are an engineer. Yeah? This is a big difference between physicists and chemists. If you talk to chemists and physicists, or even mathematicians, they will say, oh no, it's not possible. If you discuss with chemists or with physicists, mathematicians, then you very often will get the answer for your question, oh no, it's not possible. And that's all. It's fine for them that it's not possible, because they are fundamental science people. But as engineers, you have to find a solution, because the process needs to run, and it needs to run fast and safe and cheap. Yeah. And therefore, you have to find a solution, and nobody asks you if it's possible or not, because it must be possible somehow. You are responsible for making processes possible, and therefore you will always use such kind of solution that might be not totally reliable, but anyway, it's the best what you have. Yeah. So, and this is another good example for that. Everybody is using the Richard and Zaki, but everybody knows it's not very reliable, applicable here in most cases.
I have a question. Can you just explain the indice on the Richard and Zaki correlation once more?
Yes, of course. You mean these indices here, right? Yes. Yes. Right. I'm sorry, it's a little bit confusing. thank you for mentioning that. And so what we see here is S is for the swarm. This is a swarm velocity, and G means the gaseous phase. Yeah, so this is the velocity, the swarm velocity of the gaseous phase. And here we have the velocity of the gaseous phase as well, but 0 means here we have no gas hold up, so this is without gas. And for the single particle, yeah, so this PE means a single particle, and this is a single particle, let's say, superficial gas velocity. Yeah, so we use the single particle velocity, and we multiply this with 1 minus epsilon g is the gas hold up, and n is this exponent that takes into account the flow structure. Yeah, so important is swarm velocity, single particle velocity, steady single particle velocity. So if you have a single bubble and the bubble is rising without any disturbances by other bubbles, then you get the terminal velocity, the end velocity of the particle, and this is a single particle velocity here. And this single particle velocity decreases in the velocity if more particles are in the vicinity of this particle. Okay.
Okay, thank you.
You're welcome. Sorry that it's not explained here. You're right. I should write it down here somewhere that you know what these means. Sorry. Okay, and yeah, now we have already calculated diameter of the particles, the velocity of the particles. We have calculated the swarm velocity. So all these parameters are available now here. Bubble diameter, velocity, surface tension is known, diffusion coefficient is known, the gas hold up has been estimated. So with that, we can now calculate our mass transfer performance. For example, with this correlation here from Akita and Yoshida, you see here's a good agreement between experimental results and this correlation. So this can be used now to get better. But once again, have always in mind this A here. This is a critical parameter. This A is here together in this whole correlation, but actually very often it's better to look on that separately. But we know it comes here from this dr. Okay, so if this is so critical, then what can we do to get these parameters, these specific surface area? So how can we measure the bubble size distribution in reality? And I mentioned to you that we do this now in China as well. There we look from the outside into the system. Another opportunity is to use such endoscopic measurement systems, because the problem is, is this a movie? No, this is not a movie. The problem is if we start the aeration, here you see the perforated plate. There's a very typical aeration membrane that is very often used in chemical or also in chemical reactors, or also in wastewater treatment. This is a membrane where the gas is pushed through. I guess you have done the Messtechnik Praktikum in the process engineering, then you know this setup here. And this means we have usually a very high hold up of gas in the system, and then we cannot look inside because the hold up is too big. You can see this here from this endoscopic view. But if we look with an endoscope inside, then we can see single bubbles, and with the single bubbles we can evaluate them, and we can measure and calculate bubble size distributions. This is what can be done, and we can do this even for on different scales, and also for different systems in our laboratories for water, air, and of course in industry then for more critical solvent systems. And here you see, for example, a view with this endoscopic system into a bubble swarm, and you see here nicely the tiny bubbles. The bubbles that you can see here, these are reflections from other bubbles around. And now, of course, we can estimate here with this picture the size of the bubbles. We can come to the gas hold up. If we sum up all the bubbles and we know the volume that we see here, we can estimate the local gas hold up. And we can also get an information about the velocity of the bubble, because if we shoot two pictures in a certain time distance, here for example with 10 milliseconds, then you can see how the bubbles are shifting in 10 milliseconds, and this helps us to get the velocity of the bubbles. This is an example for 1 bar, 20 degrees Celsius, and only 3.3 volume percent of gas. You see, even with this tiny gas hold up, we have no chance anymore to look inside the swarm with despite the fact we have this endoscopic system that it runs. And by the way, commercial processes are usually running at much higher gas hold ups of 10, 50, 20%, up to 20%, because yeah, you know, the higher the gas hold up, the higher the interfacial area, the more mass can be transferred. So 3.3 is still very low here. So, and as mentioned, with these distance x and the time shift in between the two pictures, we can calculate the local bubble velocity. That's a simple opportunity. Yeah, and now we can measure the bubble diameter at different regions here, and to give you an insight into such a measurement and how strong the bubble size distribution, for example, depends on the position in the reactor, I would like to show you this diagram. So here we have the distribution of bubbles, and this is the average bubble diameter. And you see for this bubble column here that at the lower end area here, directly after the plate where the bubbles are performed, we have a more or less narrow bubble size distribution with an average bubble size that is a little bit smaller, here in the range of 6 millimeters. And if we go a little bit higher, so this is here 400 millimeters higher, if we measure at this position, then we see that the bubble size is more broad and also shifted to larger bubbles. This happens due to coalescence and break up. We come to a broader distribution, and because the coalescence is here more dominant, we come to larger bubbles of 7.5 millimeters in this case here for this certain system. So this means, and this is a higher gas hold up here, 10%, ambient conditions, so no pressure, and perforated plate, as mentioned before, in the water air system. So this shows that even in a column you have not only one diameter, you have a broad range of particle diameters, and even this particle diameter distribution changes over the height of the column. I guess this shows a strong complexity of this problem, and makes clear that just calculating one single diameter to design and calculate a bubble column reactor is probably not very reliable. So, but now let's have a brief break, and let's think about solutions together. What do you think is the solution for this problem that bubble columns are so difficult to be designed? Obviously, these correlations are quite critical. Do you have any idea, or do you say, do you have any recommendation, any idea, or what is used in industry, what is done to overcome this problem? Because I mean, we're talking about a huge amount of money for designing and setting up these huge plants, and a lot of and much more money related to the production phase for many years, where raw materials and energy is consumed and waste is produced. This is a massive amount of money. It's not understandable why there are so many problems, right? So what do you think? What is the most promising opportunity to come to more reliable designs. Do you have anything in mind? Maybe I have told you so much about the problems now that you are a little bit disappointed and yeah, critical against everything. So in the past, a lot of these dimensionless numbers have been used. I guess it's clear now that they are very restricted in applicability for these scale-up design. But what's about our new opportunities? We live in a new modern world with digitalization and a lot of opportunities by numerical simulation. What do you think about calculations by computers here? Yeah, actually we have also with computer calculation a lot of problems. But I guess that in future the numerical simulations will get more and more important, because even that they have some problems as well, I guess the problems are less dominant than the problems that you have with these kind of correlations. Yeah, and the reason is what I have just mentioned. You have always a strong distribution of bubble sizes, and with the bubble sizes you have a strong distribution and mass transfer performance in temperature distributions. And this is always a temporal and spatial varying situation. And it's not possible to make an average over all of that and think that with an average over all of that, what you're usually doing with these correlations, you can get correct results under all different conditions. And the only opportunity to come to this detailed insights is by numerical simulation. So probably we will go in future more stronger to numerical simulations, and probably we will accept that even the numerical simulations are not totally reliable and safe, but they are probably more reliable in future. And I guess it's already the case now. So we're now in a transition between more reliable empirical and analytical correlations and numerical, but it shifts more strongly. And from my point of view, in chemical engineering and process engineering, today we are on a point where this is right now it's shifting to more reliable numerical simulations than experimental or not experimental empirical correlations. Now, of course, it depends on the process, how complicated the process is, how complex the process is, how well known the process is. Of course, you will find a lot of processes, they are very well known. You know everything about the systems, viscosities, kinetics, and so on. Of course, in that case, conventional correlation might work. But we are in an age where we shift our energy basis, we shift our raw material basis. So conventional processes will more and more get less important, and we more and more shift to modern and new processes with new products and new raw materials. So our experiences from the past is not applicable anymore very often. And this means that we need to have more flexible correlations and opportunities of calculations, and therefore I guess strong computational fluid dynamics and process systems engineering is the only way to come to this direction. I don't know what Professor Skiborowski, our international students, is telling about this point, but I guess it's in agreement with his opinion here at this point. Okay. Any comment or question so far to this point? Okay, if not, then I would like to go further on. So we saw that these size distributions have a strong influence. Here's another example where we show that the influence of different places in Germany has an influence on bubble size distributions. So in this project here, we checked Water, Hamburg, Dresden, and Marl because they were the project partners. And even here we have strong differences, the same then with the different sizes in Europe. And if we talk about these numerical simulations now that we would like to establish, we still have the problem that we need to calculate first first the bubble size distributions, and the bubble size distributions depend on different parameters that I have already addressed. But how can a computer calculate these bubble size distribution? How can a computer calculate how large and small the different bubbles are? And for that, we need to know number density functions and balance equations and so-called kernel functions for coalescence and dispersion. And also we have to solve these equations with so-called population balance equations. So to the students on the fluid mechanic lecture, sorry if I repeat something now from yesterday, but I would like to tell this to the international students as well, because it's so important for design of bubble column reactors. And I go here a little bit more in detail so that you get also some further information how these population balance runs. So to calculate particle size distributions that are so important for the design and the prediction of bubble column reactors, we have to take into account different processes in a bubble swarm. So we have changes in bubble size, and we have this changes in bubble size by some convective transport. So bubbles of different sizes are coming into our volume or leaving our volume. We have an expansion of the gas phase due to changes in the static height. We have a change in this bubble size by mass transfer. Here, for example, nitrogen is diffusing into the bubble, therefore the bubble expands and gets larger. We might have a disintegration. So in that case here, this is a disintegration. If a vortex hits the bubble, then the bubble might be split off into different bubbles of different sizes. And the last opportunity is that we might have coalescence. And coalescence means that two bubbles are getting together. They are hitting each other and getting together, and coalescence to one larger bubble. And all these processes are taken into account, and they give us these number densities. So this means we have a number of bubbles with a certain volume V, and this is related to the class width in the volume. So we have our distribution, and then we cut the distribution in several segments of different bubble sizes, and then we count all the bubbles of a certain segment, and this is here the number of bubbles with a volume V for this segment of bubbles of volume V, and this is the width of this segment. So and then we do the balancing of all these forces, and this brings us to the number density of the bubbles, and with the number density of the bubbles we come to the surface of the area of the gas liquid system, the specific surface area. So and how do we get now the information to calculate the coalescence and breakup? And therefore experiments are necessary. Here you see very old pictures but this has been done already 20 years ago, that bubbles have been started here, 2 bubbles, and they are rising. And you can see that with these lower gas velocities, lower relative velocity of the bubbles of 10 centimeters per second, the bubbles are hitting each other, but then they are separated again. So this is called bouncing. The bubbles are get together, but they don't coalesce. They bounce, and we have still 2 bubbles here. And sorry, it goes from above to below. The time is running from above to below here. So here it starts, and the bubbles are hitting each other, but they don't coalesce. And in another case, the bubbles, and you see it's exactly the same bubble size. It's quite astonishing. Exactly the same bubble size, but the bubbles are hitting here each other, and then it comes to coalescence. And the reason why we get coalescence here is that the velocity in between the 2 bubbles, so the relative velocity between bubbles, is only 4 centimeters per second in the right-hand case, and in the left-hand case, it's 10 centimeters per second. So in other words, here the bouncing is much more intensive compared to the contact here with coalescence phase case. And now you can study this, and you can try to understand what's going up here physically. Why do we have coalescence in one case and coalescence in another case? And what comes up here is that obviously the bubble or the 2 bubbles need some time to coalesce. And the reason is that they need some time is if you have a collision here, then this means you have a liquid film in between these 2 bubbles. And first, this liquid film has to drain off until coalescence takes place. And if the contact between the bubbles is long enough that the film can drain, then you get coalescence. If the contact time is too short for the film to drain, then we have bouncing. So the time for film drain off, liquid film drain off, this is a parameter that have to be modeled. Yeah, and now we have turbulent fluctuations in the liquid phase, we have different rise velocities, and with that we found here these critical velocity, crit, this is a critical velocity that decides whether we have coalescence or bouncing. Yeah, and now we can this knowledge, we can now put this knowledge into the so-called kernel function, and this kernel function gives us a rate of coalescence divided by the number of bubbles multiplied by the bubbles with volume. So this helps us now to write down these this kernel function for coalescence kernel function. And don't worry, I don't will tell this in detail here, but this is how such a function, such a kernel might look like, where you have here the 2 diameters. Here are some adaptation factors, and here you have the critical velocity. But the physically, the important point is here these critical velocity that comes from the experimental results. And if you have adapted this kernel function here to your certain system, organic system, watery system, whatever, you can, with this function here, you can afterwards try to transfer this kernel function to another system, to another apparatus, to another geometry, to another material system. This is how it works. So here's an experimental setup where you can see how these parameters are derived experimentally. So we have a pump that pushes water here into this channel. Then bubbles are fed here with pressurized air. Gas is rising up here through this capillary. And in the 10th segment, we have a high-speed camera to measure these coalescence behavior. This is how we can do this to get the information for coalescence and breakup. Yeah, and by the way, of course, coming back to our actual project with a company in China, yeah, it would be possible to do this as well for the system in China, but the problem is you have to do this with a real material system and under the real conditions. And our process in China runs at a pressure of 80 bars and 150 degrees Celsius with a very, very dangerous and hazardous and toxic material system. So I don't want to do this in our laboratories. Yeah, it's much too dangerous. And this is why we go another way, that we directly look for the bubble size distribution in the reactor in China and compare this with our watery systems. And we don't do these extremely expensive and experiments with a strong effort, and also that might be a little bit dangerous. But it would be nice to have these information for numerical simulations, because then we would be much more flexible to calculate even other geometries and so on. But before, it was a cheap effort. If the company would pay us much more, then we would also do these kind of experiments. Here you see how it looks like. Yeah, this is here. These are the bubbles, how they are created, how they come together, and then we use some image processing to separate the bubble here, and then it's possible to calculate whether they coalesce or not. And then you get these kind of results. Here's the velocity of the bubbles, and here we have the equivalent diameters of the bubbles. And if you draw here, if the bubbles are coalescing in black or coalescing in white or only bouncing in black, then you see that there's obviously a line here that separates the bubbles that are bouncing and the bubbles that are coalescing. And this line here is directly at this velocity of about 0.075. So this is obviously the critical velocity that have to be overcome to bring the bubbles to bouncing, because then the liquid film is not fast enough to drain. Now you see this is a nice example how you can get this information and how to set up the kernel. Here you can see the pictures, how it looks like if the bubble break up. So we talked about coalescence, now we have a break up here. So we do another high-speed imaging, and here you see that the bubbles are stretched. And if the bubbles are stretched to a certain distance, then these liquid filament here rupts, and by this rupture we get two separate bubbles. And once again, here you can study this, and you can derive kernel for breakup. This is how the kernel for breakup looks like. And you can always, once again, do some experiments to show, if you have the bubble diameter, what is the influence here of breakup. And then you find that the frequency of the vortices plays a big role, and of course surface tension plays here a big role. Yeah, so you see this is how the breakup is modeled. Yeah, and then with these population balances, you can try to predict how the bubble size distribution develops in a column. So here's the bubble diameter, this is the number of bubbles, and this is the bubble size distribution calculated here with this population balance equation. And what can find with that is, and this comes back to our experiments I showed you before, directly above these perforated plate, we have a very broad bubble size distribution, a very narrow bubble size distribution, because it's given here by the diameter of the holes. And if we go further up in the column at a higher position, due to coalescence and breakup, this gets more broader, and it's shifted to larger average bubble sizes. Here we have a larger bubble size in the maximum than here, and it gets much broader due to coalescence and breakup. So you see that this population balance calculation gives us a very good agreement with our expectations and what I have showed you before with our measurements with the endoscopic system. And now you can adapt the parameters to come here to the right bubble size distribution that has been measured again. Okay, this is the same result. Here we have some comparisons between experiments and results and calculations. And this is a good opportunity, and it will help us in future probably to come to better predictions and much more reliable hold-ups, and also specific surface areas and the mass transfer performance. Okay, last slide. I already showed this to students yesterday in the fluid mechanic lecture, but I would like to show it to the international students again, because it shows the limitations of numerical simulations. Of course, you can also try to get bubble size distributions to calculate them directly with numerics. So here, for example, the whole bubble is calculated with a direct numerical simulation from my colleague of Martin Werner here in Karlsruhe. But the problem is that bubble coalescence always takes place if one computational cell is entered by two bubbles from into one cell. So if they enter the cell from both sides into one cell, then there is no opportunity for the computer anymore to distinguish between these two separated interfaces. And this means as soon as the interfaces enter into the volume, coalescence happens. Might be good because we can calculate coalescence, but the problem is that this, of course, depends on the grid. The finer the grid, the longer it takes until both interfaces enter into this volume, and this means that it is not a grid-independent solution. It's a solution, it's a coalescent that depends on the grid resolution. And this is not very physical, and this is still a problem in computational fluid dynamics and predicting gas hold-up interfacial area, and therefore the mass transfer performance. It makes the design of bubble columns still very challenging. Good. Any question related to this topic of population balance equations and predicting of hold-up and interfaces? Okay, this seems to be not the case.
I have a question. Can you just explain the kernel function once more?
The kernel function, yeah. So, yeah, as mentioned before, I don't want to go here too much into detail, and we will not ask this in the exam, and don't worry. But yeah, the kernel function is a function that gives us here the probability what kind of particle diameter will appear. And here are all the parameters that affect this diameter. Yeah, so the surface tension, diameter, the surface tension, the density of the fluid phase, the hold up, these lambda. In that case, here we talk about breakup. So this lambda is here the collision frequency. So what is the frequency in average with which these bubbles are collide? You know, so we have some physical parameters here inside, and with this physical parameters, we try to calculate the probability here of the disintegration, in this case, of the breakup. Yeah, and then we integrate here over the different diameters with this probability and with these collision frequency here in this case, and then we can come up with this bubble size distribution. Yeah.
Okay, thank you.
Just briefly explain. Of course, the reality is more complicated, but I guess it's I hope it's sufficient for you to understand how this works in principle.
Yes, that's fine for me.
Okay, there are a lot of other correlations, but all are in the same work in the same way. And a lot of has to be done here, of course, to come to more correlations. Okay, so if you have no further question, then I would like to thank you again today for your attention, that you attend here online today. And next week we will have a repetitorium, so we will wrap up the whole lectures of the module, so transport processes. So we'll wrap up the multiphase flow lecture as well as the mass transfer lecture. And yeah, I hope to see you next week in presence again. I will check with a PCR test if I'm negative next week. And I would very much appreciate if we can see us once more before these examine in presence. But let's see what the Corona crisis allows us next week. We have to think from day to day, I guess.
Excuse me, sir.
Yes.
I have one point that I want to make clear. So our prime object is that we should have the less coalescence. The less, the more is the better is the efficiency in terms of the mass transfer. Is it right?
Thank you very much for this interesting question. Yes, if you have less coalescence, then you're right. We have smaller bubbles, and smaller bubbles means larger interfacial area. I totally agree with you. Yeah. So in principle, you're totally right. But I will show you another picture here. So this means with less coalescence, we will come definitely to more homogeneous bubble flow regime here. Yeah. With larger interfacial area. But as you can see from the right-hand side, it might be also helpful to have more coalescence to get more different rising velocities and more heterogeneous bubble flow, because if it's heterogeneous, then you have better mixing. So if mixing is critical, for example, due to heat transfer, yeah, maybe you have very exothermic reaction and you have to bring the heat away, then probably this heterogeneous regime is better. Yeah, so it's not so easy to say that you should try to avoid coalescence, but it depends on the application.
But what should we choose then in terms of the mass transfer or the heat transfer? And we should have the more coalescence, or we should have the homogeneous system?
For heat transfer, to bring the heat away, it's better to have strong mixing, because then you bring the heat by convection here stronger to the walls, and then you have a more homogeneous temperature distribution compared to this, where all the liquid goes more or less upward straight.
Yes.
Yeah. So you have a much better homogenization if it's heterogeneous compared to the homogeneous regime. But related to mass transfer, it's more efficient to have this homogeneous regime, because you have a higher volume to area to volume ratio.
Yeah, sure.
Yeah.
Thank you.
You're welcome. But this was a very good question, and I hope very much that we will discuss such kind of questions much more during our student conference. This is exactly the idea of the student conference, to discuss this kind of points. Okay, any further comment or question? If not, then let's talk together tomorrow online again in the heat and mass transfer lecture, and I wish you a good afternoon, and yeah, see you online tomorrow again. Bye-bye.
Bye.
Bye bye. Thank you.
Bye.
Thank you.